sorry, let's do the clock first. The clock is an input here as well as clock. And then we have master out slave in. Sorry, this is again an input, master out slave in. And then this is the output, master in slave out. This is an output. So it has three inputs and one output. The other one, the master, should have three outputs and one input. And of course, when you connect them, if you want to connect, you take CS to CS here, clock to clock, master out, master in, slave out to this one, and this to the other one. And this is how we connect it. So if you work with SPI, this is what you should have in the microcontroller, and this is what you should have in the slave. So 4 pins in total. The CS, if you are having only one device, there is no need for CS. You can always push this to, and by the way, this CS, this is how it's defined in the protocol, the SPI. CS is active low. So you need to put 0 for it to be selected. 1 is disabled. So if you don't want this to work, you put 1. So it's active low. And remember, CS is active low for SPI. This is how it's defined in the protocol. So if you have only one device, you can always keep this 0 grounded, and that's it. So the device is always active. And then when you want to read from it, you start the clock, and then you get the data. But of course, if you have many devices, which I put here, this is an example. I mean, someone can ask question, oh, it's serial and we have four pins. So we are still using 4 pins. How does this, save a lot? Yes, it will save a lot. I mean, if you say we will transmit 4 bits, so you say, okay, it's 4 bits, it's the same like in parallel, right? But if it's 8-bit, then we are saving. If it's 16-bit, we are saving. But even with 4-bit, we are saving. We are saving a lot. So let's say that we have those devices, 3 devices, and each one is 4 bits. We'll transmit 4 bits. Do you see those 3 lines? The clock, master output serial in, and master in serial out. All devices can share those pins. And then we need a CS for each device to select. So we have 3 pins which are shared, and then we need 1 CS for each device. So for example, if you want the microcontroller first to get the data from device 1, it will put 0 here. Remember, it's active low. So it will put 0 here, we'll put 1 here, and 1 here, to make sure that the other devices will not interfere and there will be no issue on the data lines. And then we'll start the clock. Once we start the clock, this device will respond because it's the one which is active. Next, if you want to get data from the second device, you do the opposite. So you put 0 here and 1 in the first device. And then the second device will respond when you start the clock. So do you see how many lines you save if those are 4 bits? What if those are 16 bits? Or what if we have 10 of devices? So you save a lot. Is this clear? So they can share the data line and the clock, and then for each one we have a CS. And the CS from the microcontroller is basically a digital output pin. So you can use any digital output pin from the microcontroller to be your CS. But the device, the slave, should have a CS input in it to connect the digital output to it. I think we talked about this, the SPI data transfer. How does it happen? So the first step, the master first configure the clock. So it's the master who should configure the clock, and the clock can be up to 70. How do you configure it? How do you find this? I mean, you need to go to the data sheet of the slave and see which clock the slave operates with. And then based on this, what is the maximum clock that the device can operate with? So if it says the maximum is 50 megahertz, you can use a clock, any clock up to 50 megahertz. So you set it. The master should set this clock before starting the communication. I mean, you do this once when you start your code. If you have SPI, you just set the clock once, and then that's it. You go and work, and then the clock will be set. According to the SPI standard, the clock can be up to 70 megahertz. I mean, you will not find an SPI device in the market that operates with a clock more than 70 megahertz. The master sets the CS signal, and again, this is active low, remember, to select the device that it wants to read from. And then the master starts the clock pulses, so it will generate the clock. Because we have the circuitry, the clock source is within the master. So it will start the clock, and then simultaneously it will sense data with the clock. As soon as the slave receives the clock, it will start transmitting the data the other direction, right? As we explained with the shift registers. So it will transfer the data on the other direction. And that's it. This is how it works. Now, of course, you need to know, if you work with the microcontroller, you need to know how to set the clock. Connecting CS is easy. You use an output, digital output. And you should know how do you start the clock, and then how do you request the data. And usually this comes with functions, like what we did with the other, components in the microcontroller. So there are functions that will help you to do this. There are other things that need to be configured. When you work with the SPI, we have what we call a mode. And the mode is related to the clock, the clock's polarity and clock phase. We call it C pole and C phase. And again, this information, you find it in the data sheet of the SPI device that you want to use. What we mean by C pole is it active high or active low? I mean, does it work with rising edge or falling edge? And that's it. So if the C pole is 0, this means it works with rising edge. If C pole is 1, it means it works with falling edge. And then we have C phase. C phase could be as well, those are 1 bit, so it could be 0, it could be 1. If it's 0, this means the clock out of phase. I mean, do you remember the pulse trigger, flip-flops and edge trigger? Pulse trigger, we have like the data, we read it on the rising edge, but actually it is updated on the falling edge. So it's similar here. Its data is like shifted by half clock cycle. So the data here is 1. It's not the one that we have here. And the data here is this one. It's 0, going to 0, and so on. So it's shifted a little bit it's shifted by half clock cycle. Or it could be in phase, which is exactly at the same clock cycle here. So this is the data. So for the other one is like the data is on the falling edge. If we are working with the rising edge of the clock, like the data is the one that you see on the falling edge. But again, you just set the mode. You don't have to worry how the data will be read, because this is what will happen. All what you need to know is which mode your slave is operating with. And again, this information, you'll find it in the data sheet. So if it operates with, and so basically based on this, we have 4 modes: mode 0, mode 1, mode 2, mode 3. So mode 0 is 1, C pole is 0, C phase is 0. Mode 1 is 1, C pole is 0, C phase is 1, and so on. So those are the modes. I have 4 modes. So you go to the data sheet of your device, you check the mode. If it says it works with mode 0, then you need, in the slave and the master, you need to set it to mode 0. So they need to be the same mode. Otherwise, you will not get the data, the correct data. So if the slave is mode 3, you need to set it in the master mode 3. And that's it. This is all what you need to do. So you just need to know the mode and you set it to the right mode. Same for the clock. You just need to know the clock and you set it for the correct clock. But again, just to explain, this is what we mean by the mode. This is what will happen. But for you, you don't care. Working with falling edge, working with rising edge, the most important thing is to get the data. So you just use exactly the same mode. Is this clear? Now, this is in general, the SPI. So remember, we have the mode, you need to set the clock, and of course you need to know the data length, how many bits you are getting from the sensor. So all those needs to be configured before you start working. So the microcontroller that we have, the embed, has 2 ports, SPI. So it's not only one, and each one you can connect to it many devices, right? As I showed you. So we have 2. One is in pin 5, 6, and 7. And do you see the MOSI is pin 5, MISO is pin 6, and the clock is pin 7. And we have as well the other one, the second port, which is in pin 11, pin 12, and pin 13. Pin 14 is not part of this, yeah? Pin 14 is something else here, or you can use it as an analog out, an analog in, right? You know this. So we have 3 pins. As I told you, CS could be any analog output from your microcontroller. So we have those 3 pins. Those are the most important pins. And then we have the functions. That's first, if you want to use those 3 pins as SPI, because you know that pin 5, pin 6, and 7 can be configured as on digital in, can be configured as digital out. So if I want to use the SPI port, I need to configure it using this SPI, which creates a master connected to the specified pins. So this is for master. I told you the microcontroller can be a slave. We have different functions for slave, which we are going to talk about them later on. But again, we use the same port. So I configure SPI master, and then we have 3 functions. We have format. Format configure the data transmission mode and data length. So this, you specify the mode. So you specify 0 and 8, for example. So this means mode is 0 and 8 bits, or 04 or 14, depending on your device. Frequency, it says the SPI bus frequency in hertz. So you specify the frequency. And write, once you call function write to the SPI slave and return the response. So basically this it does too. When you call the function write, as soon as you call write, this will start the clock, and then the data will be transmitted. And once transmitted, it reads it. So it returns the data and you read it into a variable. So this write, it does everything. It initiates the clock, it starts the clock, it gets the data, and you read it in 8-bit. For example, if you configure 8, you read it as an 8-bit. If you configure 16, you read it as 16-bit, and so on. Those are the functions, and this does make our life very easy, to work with SPI. I will stop here. I think time is over. We'll continue next session with some examples. And then that's it for today. So I'll see you next, talk to you next session, inshallah.